Hello and welcome to lesson number 36, Matrices Part 2. In our previous video, Matrices Part 1, link in the top right, we introduced what matrices are and discussed how we can define matrices, and we talked about either defining matrices by writing out all of their elements explicitly or by writing them in terms of some common formula. After this, we then considered having two matrices, let's say matrix A and matrix B, and we considered the addition of those two matrices. We discussed the different conditions that need to be met in order for two matrices being added together to be valid, and after that, we then discussed the proper method to add two matrices together. After this, we also discussed that A plus B is equal to B plus A when you're adding two matrices together, and we discussed how you can do subtraction by considering it as negative addition. Now after this, that we finished addition, the next thing we need to cover by the natural continuation would be multiplication. And due to that, in this video what we're going to be covering is multiplication of matrices. Now considering multiplication of matrices, there are two things that we need to cover. The first is when you have a constant, let's say lambda, which is some element of the real numbers, and you multiply a matrix, let's say A, by that constant lambda. The second thing we need to consider is going to be multiplying one matrix A by another matrix B. Now in this video we're going to be considering both of these, but first off we're going to be considering the first one, which is multiplying a real constant lambda by a matrix A. And for that we're going to define a matrix A such that we're going to say let matrix A be equal to, and we'll define A as being A sub ij matrix of size m by n. Now as a refresher, what this means is that we have a matrix of size m by n, where m is the number of rows in the matrix and n is the number of columns. So basically we have m total rows like this and n total columns, and the number of intersections is equal to the number of total elements in the matrix. Now considering the thing on the inside A sub ij is a notation that we use in order to identify each of the individual elements in the matrix. I and j are counting variables, and they both go from 1 up to m and 1 up to n respectively. Now considering that, what we do is to define the very first element, which is the element at the top right, to be element 1 1. So in this case we have A sub 1 1. Now considering this, if we go up to m by n and we have m number of rows and n number of columns, then the element at the very bottom right should be A sub mn. Now considering this, if we go either horizontally or vertically, we can see we're going to either increase I or increase j. Going down, we can see since we have m total rows, the final element is going to be A sub m1. Similarly, going rightward, we can see the rightmost element here at the top right is going to be A sub 1 n, and so on. So all of the elements in between can be substituted, and so on. Now with this we can see we have properly defined an m by n matrix with m number of rows and m number of columns. Now given this, the next thing we need is a real constant lambda. So we're going to also define comma, and we're going to define a real constant lambda, which is an element of the real numbers. Now given this, lambda times a, or in fact a times lambda, since both of them are actually the same thing, lambda times a, which is also equal to a times lambda, is simply equal to the matrix lambda times A sub ij, which is again an m by n matrix. So here we can see what we have is basically, if you have lambda times A, where lambda is a constant and A is a matrix, all you have to do is to take every single element in matrix A multiplied by lambda and write the result in a new matrix. So we multiply by lambda and we get all of those elements in their same positions inside our new matrix. For example, if we consider doing 2 times, let's say 1, 3, 2, negative 4, 0, 2, something like this, and we consider multiplying 2 by this matrix, what we're essentially going to have is another 2 by 3 matrix, and in this matrix every single element is going to be equal to the corresponding matrix element in the original matrix times the constant, in this case 2. So in this case we're going to have 2 times 1 in this position, which is going to be 2. We're going to have 2 times 3 in this position, which is going to be 6. We're going to have 2 times 2 in this position, which is going to be also 4. And then we're going to have negative 4 times 2 in this position, which is going to be negative 8. We're going to have 0 times 2 in this position, which is going to be 0. And finally, we have 2 times 2, which is again 4 in this position here. So we can see the matrix 1, 3, 2, negative 4, 0, 2 multiplied by 2 is simply this matrix, which is of the same exact size, m by n, where every single element a sub ij is simply the previous element a sub ij times lambda. So we can see all you have to do is to multiply every single element by lambda. Now in this case, multiplication of a matrix by a scalar or a real constant is quite easy. The only notable things that I would like to discuss here are what happens when you multiply a matrix by 0. So considering multiplying a matrix by 0, we can see, let's say we have A, B, maybe C, D, maybe E, F, a matrix like this, a 3 by 2 matrix, and we multiply by 0, it is not equal to 0. Instead, the result we get is a matrix, and in this matrix, every single element is going to be 0 times the corresponding element in the original matrix. So we're going to have 0 times A, which is 0 here, 0 times B, which is 0 here, 0 times C, which is 0 here, 0 times D, which is 0 here, and 0 and 0. So we can see when we multiply a matrix by 0, we don't get 0. Instead, we get a null matrix of the same size in which every single element is equal to 0. So that's the only notable thing I'd like to show here. Other than that, multiplication of a matrix by a scalar is very easy to do, and in this particular case, we can see, unlike when you have addition where you need some particular conditions to be true, for multiplication of a matrix by a scalar, you do not need any special conditions. Any valid matrix A multiplied by any real number scalar lambda is going to be doable and is going to be easy to do. So we can see we can easily do lambda times A or A times lambda, where A is a matrix when lambda is a scalar. Now, moving on from this, the next thing we need to consider is multiplying a matrix by another matrix. Now, unlike lambda times A or A times lambda, where you can reverse the order and all of that, and you don't have any conditions, for multiplying one matrix A by another matrix, let's say B, there are a lot of conditions that need to be true in order for it to work. So let's go down and consider that. So we're going to say let matrix A be equal to matrix given by A sub ij, which is m by, let's say, P, and B matrix be another matrix of B sub ij of size, let's say, Q by N. Now, given two matrices like this, we can only do A matrix times B matrix, we can say, is possible if P is equal to Q. So the number of columns in the first matrix is equal to the number of rows in the second matrix. Similarly, B matrix times A matrix in the reverse order is possible if M is equal to N. Now here we can see A matrix times B matrix being possible and B matrix times A matrix being possible require different conditions. And the reason for this, one of the reasons for this, is that A matrix times B matrix and B matrix times A matrix are fundamentally different operations. Unlike in normal multiplication where you can do 2 times 3 and it's going to be equal to 3 times 2, when you're dealing with matrices, the order matters. In this case, we can see A first and B second requires the number of columns in A being equal to the number of rows in B, and if we do B first and A second, then the number of columns in B must be equal to the number of rows in A. So we can see A times B, number of columns in A, which is P, must be equal to number of rows in B, which is Q, P equals Q. Similarly, B times A, number of columns in B, which is N, must be equal to number of rows in A, which is M, so M equals N or N equals M. So we can see that these two require different conditions and fundamentally they are different. Due to this, in the general case, A times B matrix is generally not equal to B times A matrix. So we can say here, in general, it is of course possible for them to be equal. A times B matrix could be equal to B times A matrix, but in general, A times B and B times A are fundamentally different values with fundamentally different operation expressions when you have A matrix and B matrix. Now, moving on from that, once we have the condition that two matrices are multipliable, let's now consider how we multiply two matrices together. So given A times B, if we have P equals Q, the result is an M by n matrix. Similarly, if we have M equals n and we try to do B times A, then the result is going to be a P, or rather Q by P matrix. Number of rows first and then number of columns. So Q by P here, M by n here. So we're going to have a resulting matrix that's going to be, in the first case, M by n, and in the second case, Q by P. Now, let's consider the expression of this matrix. If we have A times B, as in A first, then we're going to have a resulting matrix which is going to be M by n. So we can draw that M by n like this. And considering the inside, each individual element is going to have an interesting formula for it. It is going to be equal to the sum of terms from a counting variable, let's say k equals 1, until the final value, which is the value that's equal, in this case P and Q. So the value of P or Q, which in this case I'm going to just say P. So up to the value of P, we're summing a bunch of terms from k equals 1 until k equals P. And the terms we're summing together are A sub ik and B sub kj. Now, this expression might seem a little bit complicated to you and might not make that much sense, but it will make much more sense if you do an example or two and understand what this algorithm is doing. So basically, we go from k equals 1 up to P for every single ij combination from I equals 1, j equals 1 up to I equals m, j equals n. If we do this as an example, let's say we take two matrices 2, 1, 3, 5 and 1, 2, 3, 4, and we multiply them together, we can see we have a 2 by 2 matrix here and a 2 by 2 matrix here. The number of columns of the first one is equal to the number of rows in the second one, and therefore we can multiply, and the result is going to be 2 by 2. So we can see we're going to get another 2 by 2 matrix, and considering this 2 by 2 matrix, what we're going to have on the inside is going to be the first element here times this element plus the first element here times this element. The reason for that is that if you consider this element here, this element corresponding to the first position is I equals 1, j equals 1. Now going up to our expression, if we consider I equals 1, j equals 1, we can see our term here is going to be the sum of elements from k equals 1 up to, in this case, 2, so k equals 1 up to 2 of A sub 1 comma k, B sub k comma j. Now k goes from 1 to 2, and due to that we can start with k equals 1 and move up until k equals 2. For k equals 1, we can see the two terms here are A sub 1 comma 1 and B sub 1 comma 1, since j is equal to 1. Now due to this, we can see we're going to have to multiply 2 by 1, since 2 here is the 1 comma 1 position in the first matrix, which is the A sub 1 1, and B sub 1 1 is this one here, which is the one in the position 1 comma 1 in the second matrix. So due to that, the first element of this sum is 1 times 1. Now to that, we need to add the next value, which is going to be the value when k is equal to 2, which is going to be A sub 1 2, B sub 2 1. So A sub 1 2, B sub 2 1. Now recall, A sub 1 2 corresponds to the element in the very first row but the second column, and due to that, A sub 1 2 is this element right here, first row, second column, 1. So A sub 1 2 here is 1, so we have 1 times, and B sub 2 1, since k is equal to 2, 2 1. Now considering 2 1, 2 1 is the element of B in row 2 column 1, which is going to be the element here 3. Due to that, B sub 2 1 is 3, and therefore this bit here is 3, and we have 1 times 1, which is 1, plus 1 times 3, which is 3, which gives us a total of 4. Due to that, the element in position 1 1, when we substitute I equals 1 and j equals 1, is going to be equal to 4. So if we erase all of this rough work and we write the answer, we can see in the very first position I equals 1, j equals 1, the element we get is 4. So we can write 4 here. Now, considering the next element, which is this element right here, this element is in row 1, which means that I is equal to 1, but it's in column 2, which means j equals 2. So therefore we have I equals 1, j equals 2. Now considering this, we can see if we again go to our formula, we're going to have the sum of terms from k equals 1, in this case up to 2, of a sub 1k, b sub k 2. Now, considering k2, we can see since we have 2 here, we're going to have to go on the second matrix along the second column, which is going to be this column right here. But in this case, since we have a1, we're going to still have to go along the first row in the first matrix. What we have to do here is to go along in this direction in the first matrix and this direction in the second matrix and multiply each corresponding term together and add them together. So considering k equals 1, k equals 1 is going to be corresponding to a sub 1 1 and b sub 1 2, which is going to be this element and this element multiplied together. 2 times 2 is 4, and therefore the first term here is 4. And then to that we have to add the next term, which is k equals 2 term, which going along the row in the first matrix is going to be this element right here, element number 1, and not element number 1, element 1. And going along in this direction down the second matrix, we can see 4k equals 2, we have b sub 2 2, which is going to be this element here, which is 4, and 1 times 4 is 8, and therefore the second element that we need to add together in order to get our expression is going to be equal to 8. So therefore we can say this is going to be equal to 4 plus 4, which is 8. So the second element here is 8. Now all we have to do is to continue this process for the rest of them. So considering the next one, this element right here, this is I equals 2 since we're on the second row, j equals 1 since we're on the first column. Due to that, all you have to do is to substitute I equals 2, j equals 1 and do the same exact thing. Now I equals 2 in the first matrix is corresponding to the second row. And therefore, when we're multiplying, we go along the direction of the second row. And j equals 1 is corresponding to the first column, and therefore for this thing, when we go in the second matrix b sub kj, we're going to go in this direction. So what we have to do here is to multiply this term by this term and add that to this term times this term. So if you consider the values that we have 3 times 1, 3 times 1 multiplied by 5 times 3, which is going to be 3 plus 15, which is going to be 18, and therefore the term here is 18. Now finally, for the last element, we have I equals 2, j equals 2, meaning that in our first matrix, we need to go in the second row. In the second matrix, we need to go in the second column, and therefore we need to do 3 times 2 plus 5 times 4. 3 times 2 is 6, 5 times 4 is 20, and therefore we have 20 plus 6, which is 26. And therefore the final answer here is 26. Now this was quite easy since we have a 2 by 2 matrix times a 2 by 2 matrix, but when you get to bigger matrices, you need to remember the algorithm properly and you need to properly do all of the elements and add all of the sums corresponding together in order to get each element in your resultant matrix. For example, if we have a 3 by 2 matrix like 1, 2, 3, 4, 5, 6, and we multiply it by 2 by 3 matrix, which is going to be 1. Let's switch it up. Let's do 4, 7, negative 2, 0, 1, let's say 3 maybe, like this. And we take the answer here. The first matrix is 3 by 2. The second matrix is 2 by 3. And therefore, we have the number of columns in the first matrix being equal to the number of rows in the second matrix. So we're going to have a proper matrix multiplied together. And the result here is going to be a 3 by 3 matrix. The number of rows in the first matrix and the number of columns in the second matrix. So we're going to have a 3 by 3 matrix as our result. Now, considering this matrix for the first element, we have I equals 1, j equals 1, which means we're going along the first row in the first matrix and the first column in the second matrix, which is going to be this row here and this column here. Now, considering that if we add the terms together, the first element is going to be 1 times 4, which is 4, and the second element is going to be 2 times negative 2, which is negative 4. So therefore we have 4 and a negative 4 added together, that's 0, and therefore the first element here is 0. Now, considering the next element, which is this element right here, this element is in row 1, column 2, which means we have I equals 1, j equals 2. So therefore we are going along the first row in the first matrix, but the second column in the second matrix. Now considering this, the terms that we have are 1 times 7 and 2 times 1. Adding them together, we have 1 times 7, which is 7, 2 times 1, which is 2. Added together, that's 9. And therefore the second element here is 9. Considering the next element, this is the first row, third column, which is going to be I equals 1, j equals 3. And therefore we have the first column in the first matrix and the third column in the second matrix. Considering this, we have 1 times 0, which is 0, plus 2 times 3, which is 6, and therefore the element here is 0 plus 6, which is 6. Moving on to the next one, the next element here is going to be I equals 2, since we're in the second row, j equals 1. For I equals 2, in the first matrix, we are going along the second column, so second row rather, like this. And for j equals 1, we are going along the first column like this. Now considering this, we have 3 times 4, which is 12, and 4 times negative 2, which is negative 8. So we have 12 plus negative 8, which is going to be equal to 4. And therefore the element here is 4. Now for this element, we have second column, second row, or rather, I did that wrong actually. Second row, second column, or second column, second row. And therefore, I is equal to 2 and j is equal to 2. Due to this, we need to multiply the second row of the first matrix and the second column of the second matrix. Considering this, we have 3 times 7, which is 21, and 4 times 1, which is 4. 21 plus 4 is 25, and therefore the central element is 25. For the next one, we have second row, third column, so I equals 2, j equals 3, meaning that we have second row, third column to multiply, which is going to be 3 times 0, which is 0, and 4 times 3, which is 12. So we have 0 plus 12, which is going to be 12, and therefore the element here is 12. Now for the final row, it's the same exact thing. Consider this element, third row, first column, I equals 3, j equals 1, and therefore we go third row of the first matrix, first column of the second matrix, which is going to be 5 times 4, which is 20, and 6 times negative 2, which is negative 12. 20 minus 12 is going to be 8, and therefore the element here is 8. For the next one, we have second, or rather third row, second column, which is I equals 3, j equals 2. So I equals 3, j equals 2, which is going to be 5 times 7, which is 35, plus 6 times 1, which is 6. 35 plus 6 is going to be 41, and therefore the element here is 41. And finally, we have I equals 3, j equals 3, since we're on the third row in the third column, and therefore in our matrices, we need to multiply the third row of the first matrix by the third column of the second matrix, which is going to be 5 times 0 plus 3 times 6, which is going to be 0 plus 18, and therefore we're going to have 0 plus 18, which is 18, and the final element here is going to be 18, and that is our answer. Now you can see it's the same exact algorithm, and it's always going to be the same exact algorithm. But remember, before you start applying this algorithm of a matrix, make sure that the two matrices are in fact multipliable. The number of columns in the first matrix must be equal to the number of rows in the second matrix, and then the resulting matrix is going to be having the number of rows of the first matrix and the number of columns of the second matrix. So this is all you do. You find the corresponding element, find the I and j of that element, go along the I number of rows on the first matrix, go along the j number of columns of the second matrix, and then consider multiplying in order each of the elements. So the first element in this row, first element in this column, second element in this row, second element in this column, and so on, and put the sum of those multiples in the resulting space. So in this case, for 9 is I equals 1, j equals 2, since we're in the first row, but the second column. And for I equals 1, j equals 2, we multiply the first row in the first matrix and the second column in the second matrix. And then we have 1 times 7, 2 times 1, 1 times 7 is 7, 2 times 1 is 2, added together 7 plus 2 is 9, and therefore the answer here is 9. And that is all you have to do. So now let's do a couple of examples, and then we will end the video today and move on to the next part of the video in the next lesson. So here we have a couple of examples of matrix multiplication. If you'd like to attempt them before I discuss them, you're very much welcome to. Here they are. Out of these, one of the multiplications is also not valid, so look out for that. So starting off with the first one, we have the multiplication of a 2 by 3 matrix by a 3 by 1 matrix. We can see 2 rows, 3 columns, and 3 rows and 1 column. Now considering this, the number of columns in the first matrix, which is 3, is equal to the number of rows in the second matrix, which is also 3, and therefore the two matrices are multipliable. When we multiply them, the resultant is going to be a 2 by 1 matrix, which is going to look like this. Is going to be a column matrix with only 2 entries, this entry and this entry, since we have only 2 rows and 1 column, so it's going to be a 2 by 1 matrix. Now considering this matrix, we only need to solve for I equals 1, j equals 1, and I equals 2, j equals 1. Considering the first one, we need to multiply through the first row of the first matrix and the first column of the second matrix, which is going to be 4 times 2, which is 8, plus 0 times negative 1, which is 0, plus negative 5 times 0, which is again 0. So therefore we have 8 plus 0 plus 0, which is going to be equal to 8, and therefore this element is 8. Moving on to the next one, we have I equals 2, j equals 1, which is this row times this column, which is going to be 3 times 2, which is 6, plus negative 1 times negative 1, which is positive 1, plus 7 times 0. So we have 6 plus 1 plus 0, which is going to be 7, and therefore the element here is 7. This is our answer for the first question, 8 and 7. Now, moving on to the next one, we can see we're given a 4 by 2 and a 2 by 3. Considering these two, the first matrix has columns of 2 and the second matrix has 2 rows, and therefore the number of columns in the first matrix and the number of rows in the second matrix are equal, and therefore the two are multipliable. And the resultant is going to be a 4 by 3 matrix. It's going to be a big matrix like this, where we have 1, 2, 3, 4 rows and 1, 2, 3 columns. Now considering this, if we go through, the first element is going to be first row, first column, which is going to be 0 times 2 and 2 times 3, which is going to be 0 plus 6, which is 6. The second element here is going to be first row, second column, which is going to be 0 times negative 3 and 2 times 0, which is going to be 0, and therefore we have 0 in the second element here. The third one, which is going to be first row, third column, which is 0 times 1 and 2 times 4, which is 8, plus 0, which is going to be 8, and therefore the element here is 8. Moving on to the second row, in the second row we have second row times first column, which is 3 times 2, which is 6, minus 9 times 3, which is negative 27, 6 minus 27 is negative 21, and therefore second row first column is negative 21. Moving on, the next element is going to be the second row second column, which is going to be second row times second column, which is 3 times negative 3, which is negative 9, and negative 9 times 0, which is 0. So we have negative 9 plus 0, which is negative 9, and therefore here we have negative 9. Moving on, this element is going to be second row and third column, which is going to be 3 times 1, which is 3, minus 9 times 4, which is negative 36, and therefore we have negative 36, plus 3, which is going to be negative 33. Moving on to the third row, we have third row times first column, which is negative 1, times 2, which is negative 2, and 0 times 3, which is 0. So we have negative 2, which means the element here is negative 2. Moving on, the next element is going to be this times this, which is going to be negative 1 times negative 3, which is positive 3, and 0. So therefore we have positive 3. So we can just write 3. The last element here is row 3, column 3, which is going to be third row times third column, which is negative 1 times 1, which is negative 1, and 0 times 4, which is 0. So there we have negative 1 plus 0, which is going to be negative 1. For the last column, or last row rather, row number 4, first element is going to be this times this, which is 5 times 2, 10, plus 6 times 3, 18. 18 plus 10 is 28, so the element here is 28, and then we're going to have this times this, which is going to be 5 times negative 3, negative 15, 6 times 0, 0, negative 15 plus 0 is going to be equal to negative 15, and the final element here is this times this, which is 5 times 1, 5, plus 6 times 4, 24. 24 plus 5 is 29, so the final element here is 29, and we can see this 4 by 3 matrix is going to be our solution. Now for the next one, we can see we have a 2 by 3 matrix multiplied by a 2 by 3 matrix. In this matrix, we can see the first matrix has 3 columns, while the second matrix does not have 3 rows, it instead has 2. Due to this, we can say the two matrices are not multipliable. So we can say is not multipliable. We simply cannot multiply the two matrices together in order to get a resultant matrix. So we'll just ignore it and move on to the next one. This is an impossible case. Now moving on to the last question, we can see we have a 1 by 3 matrix multiplied by 3 by 2 matrix. Here we can see 3 and 3 here. We have 3 columns here and 3 rows here, and therefore the two matrices are multiplicable, and when we multiply, the resultant is going to be a 1 by 2 matrix. So we have a 1 by 2 row matrix like this. One element here, one element here. This is I equals 1, j equals 1, and this is I equals 1, j equals 2. And therefore we have the first element here being this row times this column, which is going to be 1 times 2, which is 2. 2 times negative 4, which is negative 8. So 2 plus negative 8 is negative 6. And 3 times 1, which is 3. Negative 6 plus 3 is negative 3. So the element here is negative 3. For this element, we're going to multiply this row by this column, which is going to be 1 times 5, which is 5. 2 times 3, which is 6. And 3 times 0, which is 0. So we have 5 plus 6, which is 11. And therefore the element here is 11. Now, that is going to be all for this video. I highly recommend that you yourself try other examples like this. Find random matrices, search Google or something, search an AI language model or something for examples, or just do randomly write a bunch of equations and try to solve these kinds of matrix problems by either multiplying two matrices together, or you could try multiplying 3 matrices together, and you might find some interesting things when you multiply 3 matrices together. Now within our syllabus, we actually don't really have multiplication of 3 matrices like A times B times C within them. If we have anything, it will be solving A times B first in a separate question and then substituting that into here later and multiplying by C. So for now, this is going to be all I'm going to do. I highly recommend that you yourself make a bunch of different matrix problems and try solving them by yourself. But for now, that is going to be the end of this video. I hope you enjoyed. If you have any feedback, post them in the comments down below. Thank you for watching and goodbye.